We've got Darin Morgan here joining us, guys. Talk about going heavy hitters right at the start. And he's got a laptop, and he's going to do a presentation. I'm like, Darin, what's it about? Hemi hand grenades? That's right up my alley.
I can see this. I'm like, okay, I'm all in. Yeah, so it's like, yes, we're starting off the day full horsepower, right? Engines making power, and then we got this guy, because airflow is what it's all about. We can't burn it if you don't get it in. And you're the induction guru, so I'm going to shut up and listen.
Yeah,
and learn.
exactly.
Okay.
This, Dodge Hemi Challenge, U.S. Nationals, one of the biggest single one-off events for cars that were never designed to go that fast, going well beyond the dreamed capability when they were manufactured. It's one of the greatest events in all of the drag racing world. Happens each year at Indy. Tell us a little bit more.
Factory engines were never meant to do what we're doing, ever. We push them to their limits, and then a little bit more, and then a little bit more, and then a little bit more, until basically they end up as eggshells. And I'm going to go through not only the foundry process of casting these cylinder heads, which are cast at Profiler now. I'm going to show the cores and everything else. But we're going to go through all the machining techniques that we use and why we do what we do as far as developing these engines, primarily the cylinder heads and intake manifold, which is my job.
Okay.
So this is the foundry. This is at Profiler, and this is a core box. You get to see the intake cores going into the core box itself, and the exhaust cores. And there in the center you see the water jacket. Now these cores are painstakingly put together, glued together. And this is the factory cylinder head. This is what, if you call up Mopar and you ask for a 426 aluminum cylinder head, this is what you're going to get. This is how they are cast. And the Super Stock Hemi rules dictate that you must use the factory casting. You can't use an aftermarket casting. They have to be basically the same exact thing that you could buy in 1964 or 1968. But Mopar, in their infinite wisdom, has developed race parts for this class. The blocks are now thicker, stronger, and heavier, I might say, as well as the cylinder heads themselves are also thicker, which allows us a little more latitude to push them even further.
So it's the same design, but you just are adding a little more material when they're pouring it.
Yeah. Yeah, I'll show some actual cutaways of the cylinder head and the relative thicknesses throughout and show you what we go through. This is how I like to start with a cylinder head. When I'm developing anything for any class, I want the raw cylinder head. And normally you can only buy the cylinder heads with seats and guides already installed. Well, that for competition use is limiting, because a lot of times what we'll have to do is qualify the core. So basically you have a core with a water jacket and the ports going through. You have to basically machine this thing up to where the thicknesses in certain areas are sufficient enough to do what you do. So in other words, if you're just going to square the whole thing up and machine it like the Foundry does, that would be insufficient for what we would use it for. So what we'll do is we'll actually jog the head fore or aft to make certain walls thicker or thinner to optimize the situation.
And that's just because when you pour something, they're not all the same.
They're not all the same. And there's shrinkage and core shift. In other words, the water jacket itself is a very thin. Let me back up here a little bit. The center, what you see there in the center is the actual water jacket core. When you pour the aluminum in there, that's going to be the hollow area. And you can see the little holes there. That's for the valve guides or the spark plug hole. Now that is a very fragile piece, and if it's not glued down properly, what will happen is when you pour the aluminum in, it will float up on one side or the other, or the whole thing will float up. So these things are all glued in place. And if you get a water, and this is pretty common, or used to be very common, called water jacket core float. You pour the aluminum in there and the sand would float up. So that makes your roof thin and your floor thick, or vice versa. So now they've pretty much done away with all that. They've been able to cast these things uniformly and get the water jackets and everything small enough. Now, nowadays we have 3D printing. You know, we can 3D print water jacket cores that were absolutely impossible to make 10 years ago. They're very fragile, very small. It gives us thick walls everywhere. It allows us to do things that we couldn't do. But in this casting, that's not allowed. It has to be a factory OEM casting for this class. I'm going to go in a little bit about the differences between the modern 5.7 Hemi and the old 426, 64, 68 Hemis. And what they've done to actually increase its efficiency and power overall. Now, the engines, some of the, like the drag pack engines, the Elephant engines that we build at BS, those things will make anywhere from 1,500 to 1,700 horsepower supercharged. And that's a standard, standard drag pack engine, 1,200, 1,300 horsepower, that's nothing. I mean, yeah.
It's throwing out 1,500, 1,700.
The reason you can squeeze that much efficiency out of these things, that would be difficult to do with the old Hemi, is because they've optimized the chamber design. And here you see that the chamber isn't the old 45-degree hemispherical, just a globe cut off. It's a hemispherical chamber. Even at Glidden's, what we would do with the Ford Hemi heads is weld the combustion chambers up and make them this exact shape. I mean, this is what he did.
Standing the valves up more and basically making
We couldn't stand the valves up. We didn't stand the valves up then.
Okay.
But what we did was we concentrated more on the chamber than anything else. And now we have 2 spark plugs per cylinder, which in the Hemi is mandatory if you're going to squeeze any level of efficiency out of this thing. Because if you have a big chamber and the spark plug's on one side, the flame propagation is 360 degrees away from the plug, and then it moves across the combustion chamber. So if you have a lean or spot in that combustion chamber and that flame front moves across that chamber and pre-compresses that lean part, bang, off it goes. But if you have 2 flame fronts, the ignition timing is 10 degrees less, the flame front is much faster, and the efficiency is greatly increased. And here, this is what you would buy if you just bought a 5.7 chamber. And you can see that everything is brought in. The chamber surface area to volume ratio is reduced. It's down as much as you possibly can. As opposed to, this is a prototype I'm working on right now. We're doing 2 sets of iron heads and 2 sets of aluminum cylinder heads for individuals in this class. And this is a very big chamber. Very
giant.
Inefficient chamber. And that is one of the problems with the hemispherical cylinder head design. Its assets are that it has equal pressure recovery around the valve. When that valve opens, it sees open area all the way around it. And the decrease in airspeed is uniform all the way around it. So it has a higher CFM per square inch of valve area. I mean, it flows more air per unit area than any other cylinder head ever designed, period.
That's its strength.
That's its strength. Exactly.
Okay.
That's its strength.
Not the fact that it's this giant globe.
But then you have to put up with the fact that the chamber's surface area acts like a quench. It tries to put the fire out, So what you do is you will CNC this dome or this combustion chamber into the cylinder head, and then you transverse that onto the dome. And then what you will do is you will manipulate that shape to increase the flame travel in these chambers. So instead of having a perfect hemisphere that fits up into the chamber, what you'll do is you'll bring the sides in and the top down. So what you're doing is you're literally forming this crevice that opens at the top, and you're trying to harness all the air-fuel mixture right over that plug as much as you can. And by bringing the sides in, you're shooting the air-fuel mixture up to the plug.
To push it in.
Yeah, and you're talking 5-10 horsepower here. You're playing with up at 9,600 RPM. I mean, just getting it just a little wrong has a big effect.
Is it like almost like a giant quench? You're trying to push everything into that area near the spark plug so you can bang it out and you get that great burn.
Yeah. Try.
That's cool, man.
Try.
Yeah.
We
Try. Yeah.
I mean, as opposed to like a Pro Stock engine with a 45, 46 cc combustion chamber with all the flat area that just shoves everything to the bore center. This is really, really difficult. It takes an immense amount of time and energy to produce these cylinder heads, up to 150 hours a set.
Whoa.
Yeah. And I'll get into the welding later. This is what I have to deal with. It's basically an eggshell from the very get-go. This is a cross-section of a Hemi, a stock 426 Hemi cylinder head. As you can see, the wall thickness it's not gracious, they're thin. So you start porting on this thing, you're going to end up with very thin walls. And this is why I call it a hand grenade, because by the time I'm done with this, you're going to be shocked at how little is left. Basically what I do, the super stock rules dictate that you have to maintain stock intake port CCs. That intake port, exhaust port, and the combustion chamber have to hold the same volume as the stock engine did. So how am I going to make this port bigger in order to flow more air?
So
Yet still
the
maintain
total amount of CCs has to be the exact same.
Exact same.
So I'm assuming you're going to try to make a giant funnel out of that to increase airspeed.
I try.
You try.
I don't get there, but I try.
Because you don't have enough material.
I don't have enough material. So what we have to do is, if that runner has to hold the same volume as a stock engine, if you sink the valve into the cylinder head, you can enlarge the cross-sectional area, right? And thereby it holds. If you mill the intake flange, you can again enlarge that cross-sectional area. There's no way to make this cross-sectional area large enough to support the flow potential and RPM potential of the engine. There's no way to get there. 50% of my time on a prototype is working out trying to get the cross-sectional area as even as I can. In a perfect world, what you would want is the throat to be the fastest part. And then everything, like you said, to funnel up. It gets bigger as it goes out. You can't accomplish that here. It's absolutely impossible.
Ooh.
This is a 5.7. This is the modern Hemi.
So this is the factory.
Yeah, this is the factory 5.7 Hemi, a cross-section. So what they've done was, instead of the old 45-degree Hemi, they've stood the valves up, which shrinks the combustion chamber volume, increases flame travel, flame speed. So there they've gotten some efficiency as well. And the valve train itself all works out. So now we're going to get into volume and length. Back in the 60s and 70s and even 80s, people would say, well, I have a 355 cc port, or I have a 300 cc port. That metric is no longer used. It cannot be used because back then you had an OEM cylinder head. Let's take a 23-degree small block Chevy. Okay? Well, you're not going to modify that thing too much. And the bigger you can make it, the more power or the RPM potential of the engine is going to go up. The problem is, back then, you couldn't make them big enough. So everybody started bragging about, well, I have a 220 cc or a 225 cc. And what that related to was the RPM potential of the engine. And then the aftermarket in the 90s allowed us to vary cylinder head design wildly. We could do anything we want. And now there's a plethora of cylinder head designs with different length runners. So you can't say, well, I have a 355 cc runner anymore. Because let's just take, for instance, a standard big block Chevy. You go buy a standard conventional big block Chevy cylinder head from Brodix versus the newer 20-degree cylinder heads from Brodix. Well, the 20-degree cylinder head is 5/8 of an inch longer port length.
5/8 longer?
Yeah, than the original conventional cylinder head. So a 355 cc port in a standard conventional head would be 400 cc's in a 20 degree. But cross-sectionally, airspeed-wise and cross-sectionally, it's the same. So this is where people will get off on that.
Sounds like CCs is like RA for surface finish. It's a number, but it doesn't tell you the whole story.
And here what I've done is I have taken an 18-degree, an SB2, and a Brodix canted valve. Mm-hmm. Both cylinder heads hold the same volume. Both cylinder heads flow exactly the same, but their length differs quite a bit. So if you go to the far right of this depiction, you'll see that the airspeed varies wildly. So if you look at this, the 18-degree can hit 9,000 RPM. The SB2 would be about 8,800, and that Brodix canted valve would be lucky to get past 7,000 RPM.
Okay.
Here's a depiction of like a big block head. The Brodix Big Duke both versus a Profiler spread port. Both have the same volume. Both flow the same amount. The average cross-sectional area varies drastically. There's 500 RPM potential difference between these two cylinder heads just using CCs to base a cylinder head on. So that metric can no longer be used. So now we'll get into how much power can you get out of a 426 Hemi? Well, they're not actually 430 or 426. They're actually 435 cubic inches because you're allowed 60 thousandths overbore and 5 thousandths plus stroke. And if you give rules to a racer, he's going to push them.
Right.
Yeah.
Yeah.
So if they allow you 5 thousandths over stroke, that's exactly where you're going to go.
Yeah, exactly.
And
Yeah.
if they allow you 60,000, that's exactly where you're going to go.
Yeah.
Because if you're making 2 horsepower per cubic inch, every cubic inch is
matters.
2 more horsepower.
Right. Yeah. Exactly. Yeah.
So what I did is you can do this simple calculation for a 435 cubic inch motor. These engines do make peak power at 8,800. And they're limited at 8,800. You can't get past that. And I'll explain why here in a little bit. But the required airflow to attain 8,800 RPM is 473 CFM. Now these engines have a 250 stock valve. And they flow 475 CFM. Because a Hemi is the most efficient flowing port that you could possibly get. This is what they actually flow on the cylinder head. Now, when I say I take most of my time in developing the ports, getting that area as big as I can, usually in a normal port design, you'll have the throat at like, let's say 90% of the valve, and the opening upstream would be like 100 or 105% of the valve. It would increase and taper. And here, you can't get there. You just can't get there. I spend all my time just trying to make the average cross-sectional area the same as the throat.
Oh, just keeping it the same.
Yeah.
So it doesn't taper
because of it's
small.
Yeah. Because you don't want anything upstream smaller than that throat.
Right.
So that is the limiting factor right there. This is why these engines are RPM limited. They are cross-sectional area choked off. Once the airspeed reaches a certain point, that's it. That's where it's going to make peak power, and the whole game is to try to carry it out. Try to carry that peak power as far as you possibly can. 20 years ago, they were spinning these things 9,000 RPM, and now, because of advances in valve train, we can shift them at 9,600. But doing that comes at a severe cost.
Price, yeah.
Yeah. So let's look at a standard cylinder head. If lift LD ratio here, you noticed off to the right of this LD, that's lift to diameter. In other words, if you have a 250 valve and lift it 0.23 times that diameter, it should flow about 90, 91 CFM per square inch of area.
Got it.
Okay. And if you lift it 0.4 the LD, it should move anywhere from 117 to 118 CFM. That's with any cylinder head. It doesn't matter if it's a wedge, a cannon valve, or anything else. Other than a Hemi, that's it. You aren't getting any more than
That's
118.
just the choke of the area, right?
Yeah. Yeah. Once you reach a certain airspeed, that is the limiting factor. And any cannon valve engine, if that's the target, to hit 118 CFM per square inch of valve area by 0.4 LD ratio.
Okay.
So if anybody wants to know how much flow can you actually get out of a cylinder head, now you have it. Now the Hemi, being the most efficient flowing design ever conceived by man, that will actually flow 375 at 0.23 or 0.25. So it's 94 CFM per square inch of valve area. And they'll hit 119 to 120 CFM per square inch of valve area up there at 0.4, which is astounding. You would never be able to achieve that with a cannon valve engine or anything like other than that. But that's the limit. Now, if I could actually take that limited 475 cubic inch or 475 CFM that I'm getting out of the cylinder head and make everything upstream of the valve perfectly sized, like I can in Comp Eliminator or Pro Stock or any other class, then the engine would peak power at 9650 and you would shift it at 10.5. So that, if I could do it, but I can't. So that shows you how limiting that port cross-sectional area is. So, in an unlimited, I could shift it at 10.5, and now that this cross-sectional area is so small, it knocks it back down to 96.
And that's just because of the velocity.
Yes.
Because you can't go faster than that.
Yeah, it hits what's called the mean inlet Mach number. It hits 690 feet per second at that point. And once you hit that point, they call it a choke. It is a airflow choke, but it doesn't. The power doesn't stop. It just stops increasing. So basically, the power band will come up and nose over, and the idea is to carry that out as far as you can.
Right.
So let's say you're making peak power. They'll make about 1,000 to 1,025 at 8,800. If you can carry that out and still have 990 horsepower, 500 RPMs later, you can move the whole power band up and average more power. So you're basically dropping back down into 100 more horsepower because you've raised that whole thing up.
Yeah. You're trying to limit the losses at this point.
Yeah. One of the other limitations is the valve train. This is one of the reasons why these things are hand grenades. Here you
okay, so the one on the left is the original 426 factory. The one on the right is the modern 5.7 factory engine.
Yes.
Okay.
And you can see the valves are stood up. Mm-hmm. But what they've done in the modern cylinder head is you'll see that the lifter bores, the cam is raised up way in the block, and the lifter bores are splayed out. Mm-hmm. So what that does is it makes the valve train what we call in plane. In other words, the rockers and everything are directly in plane with each other. Where the old 426 Hemis had the push rod way down the block, and everything is out of plane. So managing the valve train dynamics on these engines has always been dicey at best. And if it wasn't for Jessel really working with these racers, we would never be able to hit 9600. And plus, we have two push rods going right by the port.
Right.
So that limits me as well.
And now you have another physical limit. You have your rule maker, then you got that daggone push rod hanging out over there.
And the push rods actually protrude into the port.
Yeah.
And the newer valve trains, they've moved the push rods out, but that has a detrimental effect because you're moving things out of plane again.
Yeah.
You know, it's like, okay, do I sacrifice the valve train to get the port volume, or do I get the port volume and sacrifice the port for the valve train?
Yeah. What side of the sword do you want to fall on? You're going to bleed either way.
This is a stock valve train, basically. And you see everything is, you know, you couldn't get that past about 7,800 RPM without incurring some major issues.
Just a lot of mass there, too.
Oh, yeah.
I mean, not only do you have the geometry issues, there's a lot of mass in this. Yeah.
This picture, it's hard to see, but, you know, you have steel, you have a long rocker arm on the exhaust, so you have a steel rocker arm that's just a little razor thin all the way. This valve train took 1.5 years to develop. And what you don't see here is the standard Hemi valve train has 5 bolts going down right through the center. And that's all that's holding it.
Just 5.
Yeah, so you have a valve train this wide with push rods on both sides held right down the middle. So the whole thing wants to sit there at high RPM.
You don't need to be Danny Jessel to realize that's a bad thing.
That's a bad thing. So later on, iterations used the extra spark plug hole as a stand and triangulated 10 bolts. That has 22 bolts.
22?
Yeah.
Wow.
That has 4 pedestal stands, bars underneath the intake, and things you can't even see.
That's cool.
That took the engine from 9,400 RPM stable to 9,650.
Yeah.
And that
just doing just doing that.
That's the difference between 159 miles an hour and 160/150.
How about that?
Unreal.
Yeah.
But what we had to accomplish that, raising the RPM range, is what has made these things hand grenades. I mean, racing one of these engines is like pulling the pin on a grenade and just playing with the trigger.
And that's why people show up to Thursday at the U.S. Nationals to see these cars. In this race, there are so many people, and you deal with them on a regular basis. They spend a ton of money, a ton of time, a lot of effort goes into it for one event a year. And then the car goes away, and they go back to work and try to figure it out again. And that's why you got to go to the U.S. Nationals, folks.
Yeah. Spending $80,000, $100,000 on one of these engines is not uncommon. I mean, it's just the amount of work that goes into it. I mean, just welding them alone, you've got 2,000 in welding, and then 100, 150 hours. You've got $16,000, $17,000 in labor and welding before you even buy parts. So,
you want to play the big boy table? There's your ante.
Well, exactly.
The new 5.7, shorter push rods, better valve train alignment, everything's in plane. And now you look at the old block. The push rods are next to the cylinder. You have a lifter like this. You have a push rod leaning over. You have, everything is not right. So everything you do in this area is made to optimize. Move the bores over a little bit. Get rid of some of that angle differential. And the old blocks have to use a stock core cam, which is also limiting. And the newer blocks, you can put a 60 millimeter cam in those things.
Oh, wow. Okay.
So some of the Elephants, some of the bigger engines, you can put 60 millimeters in there, no problem. So that allows you to, you have a better valve train, able to lift the valve higher, and you have a longer rocker arm ratio, fulcrum length.
Right.
Because the fulcrum length on a stock Hemi is really, really short. So let me go to the board real quick.
Yeah, go for it.
Isn't this great?
Oh, this is awesome. This is a master class.
Like,
I hope y'all are enjoying this because I'm loving this.
Yeah, this is out of control. We got Darin Morgan at a whiteboard.
Right, this is cool. This is so cool, yeah.
So if you look at the arc on this as opposed to this, so basically you've got this much on the valve stem. That roller will start move this way and then all the way to the other end and then move back with a short rocker arm because you have only so much arc to work with. So as you're opening the valve, this tip is moving across the valve and then moving back. And at a certain point, you're going to stand that rocker arm up, and any more motion is not going to do anything. All you're doing is moving that roller back on the valve and wasted motion. So on the newer stuff, you can get 1-inch lift. And on this stuff, 950, 965 lift is about as much as you can squeeze out of it. So that's another limiting factor. Because the 60 millimeter cores, as opposed to this, will automatically raise the RPM range 1,000 RPM, just with increased lift, decreased seat duration, increased valve speed. You know, you do all that, that's 1,000 RPM.
Just 1,000 RPM.
Just 1,000.
Yeah.
And you're talking about...
This is old school, and I love this now. We got some stuff in the port. Here we go.
That 1,000 RPM nets 125 plus horsepower.
Yeah.
Yeah.
Yeah, just
easily.
Yeah.
So when I say you have $2,000 worth of welding and brazing in these cylinder heads before you even start work on them. Now, by the way, this is an art form. Brazing these cylinder heads up, or I've had some cast iron welded before. But most of the guys that do this are in their 80s and 90s, you know, or retired. Right. It's almost impossible to find people to do this anymore correctly, because this cylinder has to be brought up to temperature until it's cherry red, and then welded, and then brought down over a period of time very slowly. And if it's not done correctly, it will cause stress in the casting and crack it. And then all your work's for nothing.
And it's already an egg to begin with.
Yeah. You're going to see an eggshell here.
So this is like a Fabergé. This is basically a Fabergé egg you're building here.
This is what I start with. Now, I want you to notice the intake flange here. Mm-hmm. It's all solid across there, and we even have a indent or a chamfer where the intake bolts are. This is the exhaust side of the cylinder head, and we raise the ports up about 3/4 of an inch on the exhaust side. Now, these are the iron heads. The iron heads take more labor than the aluminum heads do.
Yeah.
When NHRA allowed us to run aluminum cylinder heads, I was like giddy because that allows repairability. And the cast iron heads, if you lose a bearing and that piston hits, it's gone. It's history. It shatters. If you lose a valve, it shatters. Anything happens, these cylinder heads shatters. In 150 hours, it's gone.
Out. Yeah.
They are not repairable. And this is why we do 2, 3, 4 sets at a time.
So you have a spare.
Yeah. You got to have spares. You won't complete a season without spares. I angle mill the flange, and again, the whole idea is to mill that intake flange to gain volume so I can increase that cross-sectional area. I will take that flange and mill it 3/4 of an inch, and then in 150. Now, the NHRA stock rules dictate that the valve cover bolt, the stock valve cover bolt, you cannot mill into those threads. That's my limit.
So you go as far as you can to get to those threads, and that's where you stop.
So if you just milled the flange, you would get half of the volume. So you angle mill it to get that big chunk out of it. And what that does, this is a raising of the exhaust port by the time it's all done. And by the time you get done with that, you can see the flange has holes in it. And those bolts holding the intake manifold on, there's about 5 threads.
That's just enough, huh?
And you can see where it's just protruded into that bolt hole, which they allow it legally. The bolt hole's at an angle, and you can mill into those, but you can't mill into the top and move it. And believe me, people do that. People will weld up that bolt hole and move it in so they could get more off of the intake flange. And when there was some creative interpretation of the rule book back in the late 90s, early 2000s, people were milling the entire intake flange off of these cylinder heads and building it into the manifold like an FE Ford.
Got it, yeah.
Yeah, which is completely, they've made that illegal, which it is.
So the one on the left that's not factory as cast, right? No.
I'm sorry, I'm not following.
The photo on the left, the port on the left compared to the port on the right.
That's welded up. The whole floor is welded up.
That's welding it up. Then the one on the right is the one as finished once you've opened it all up.
I'm still working on that, but it's close to finished.
Close to finished.
Yeah.
Look at that. I can't believe we're seeing this.
This is awesome.
It's like, I'm surprised. Are you allowed to be doing this, Darin?
He's doing it. Don't stop him. It's like Scooter says, right? The more you tell, the more you sell. So let him keep talking.
Here we go.
This is basic. You know, guys like Westcott and guys Barton, and they've been doing this for 40 years. This is old hat to them. I'm not telling them anything new.
Yeah.
But for the people who don't know actually what goes into these, and you know, you see the epoxy work in there, and I will spend probably a week on this port just trying to get the cross-sectional area to not have a choke in it somewhere and still maintain the airflow.
Just a question real quick on that. Go back, if you don't mind. Would you consider that, because obviously what you guys do at BES, I mean, y'all are covering everything, right? Obviously this is a specialty, but you guys do everything.
We work on everything from Briggs and Strattons to Bugattis. It doesn't matter.
There you go. That's what I was thinking. Would you consider this kind of work almost more artisan, old school? Cause I remember when my dad first had his NASCAR team and they were building engines, watching guys like Gail Pauley who worked for Dad. He was doing this kind of stuff, but that was, you know, almost 40 years ago. Now you walk in and you see stuff. My time at Gibbs, and everything's CNC'd.
Yeah.
You're not doing this anymore. So this kind of feels like this is like old world artisan craftsman type work.
Yeah, this is a rarity nowadays.
Okay.
Well, and it's all because you're dealing with the rule book.
Yeah.
Like all of this is related to the NHRA stock, super stock rule book, which the whole point of it, and you know, the fastest museum in the world is an NHRA stock, super stock race, automotive museum, because they have to be what the factory put out to a point.
Yeah.
And like
stock valve size, stock port volumes.
And what you're doing with that the valve cover hole, like, well, it's got to be in the, okay, well, we're just going to cut the bottom off of it. Excuse me.
It's a game of how far we can push.
That's why so many people get out there at 8 in the morning to watch stock and super stock. And this is the highest level Hemi challenge at the U.S. Nationals, but it's amazing. And call it artisan, old world, whatever. This is what they have to do to circumvent the rules.
To have the advantage, right? It's like how much further can I push it?
If you are going to win races and set world records, you have to be willing to do what nobody else will do or knows how to do.
Boom, that's it right there. That's what we do this for. The whole expo is that right there.
T-shirt.
And the days of doing things that other people don't know how to do are greatly decreased. So that increases, you have to work harder and longer.
Amazing.
Yeah. All right.
Keep going. Yeah. And for those that are wondering, typically our bits go about 20 minutes. This is like all hands on deck. We're getting to the end of this regardless. Like this is
however long it takes.
Unbelievable start what we're seeing here.
Yeah.
So the welding, you can see over there on the left, the welding of the intake ports. I'll have about 8 hours of welding to these cylinder heads before I start. And, the rod you use and how you preheat or don't heat or quench that cylinder head, these things warp out. So you have to be really, really careful when you weld these things because they're already thin wall castings. It's not like you're starting with something, that's not going to warp out 20, 30, 40 thousandths by the time you're done. And the valve train, getting these things to wind up, working on that valve train, that's the last decade, that's where it's been at.
Valve train.
Yeah. Because 9400, you could go to 9500 and all the parts would end up in your lap or on the racetrack. I mean, it's finite. I mean, these things, if you overshift this engine, the engine comes out of the car. If you make another run, boom. If you hit that 10,000 RPM limiter, you have overstressed the valves I'm about to show you. And what will happen is the head will shrink and they'll pull into the port. Because if the valve train goes out of, if it goes chaotic, which it has a finite limit, and that limit is about 9650, 9700 RPM. And if you hit that 10,000 RPM limit and things start going crazy, it will destroy the valve integrity, the structural integrity of the valve, and it will drop about the next pass, 90% chance. Now, a stock valve is to the left, and the modified valve is to the right. Now, this is, again, how we gain another 400 RPM, with hollow stem stainless valves.
Got it.
Now, also, if you think about it, I have to maintain that port volume.
Okay.
You see it.
Yes, sir, I do.
The tulip valve takes up volume, allows me to increase the cross-sectional area. Now, a flat valve will flow better, but I can't use it. So now I have to work that give and take of, okay, how much tulip can I put in there without hurting the airflow and gain the amount of area I need to make that cross-sectional area the same as the throat. That's the game.
That's awesome.
Now the back cuts on that valve, we have to, again, push it to the limit. So the throats are past what we would consider optimal because we have to make them bigger. So we're actually hurting the discharge coefficient enough, a little bit, to gain enough area to raise the power band. We're working on that razor's edge. So the big increased back cuts help turn the air. So with that big throat, you can't set the air up to turn around the valve. So you put those back cuts on there to cut that air to try to move it. This is basically an aftermarket stock Hemi valve. It weighs 147 grams. If you tried to take that past 9,000 RPM, you have problems. Now, if you make it a hollow stem valve, reduce 2 degrees on there, and make it about 150 thick at the base of the radius, yeah, the valve itself is an eggshell. So that's why if you overstress the engine and send that valve train chaotic, it's done. And again, you could do it once. And I seen it at the racetrack twice. Now, my brother was the engine builder at Rare Morrison who built all these. And I did all the heads and manifolds, which we'll get into here a little bit. At the racetrack, he hit the 10-2 limiter twice. And my brother said, get it out of the car. it's going to blow up. He didn't make it out of second gear the next pass. And the pistons were in the oil pan. I mean, this is why I call them hand grenades. And you have a finite set of runs on the cylinder heads too, because as you sync those valves, you say you make run after run after run, you have to freshen them up, you have to go in and recut the seats. Well, that moves the valves in a little bit. So that affects the valve train. You're dealing with multiple compound angles within a Hemi. And any change you make on one of those dimensions is going to have profound effects downrange on the valve train, rocker arm geometry, or what have you. So you're working in this small little window. This is a standard 426 Hemi cross-ram manifold. Now, NHRA rules dictate that the carb spacing must remain stock. So you still have to maintain that stagger, which is a major problem, because the cylinder-to-cylinder variation on these engines is profound. I mean, you have to stagger jet. I've seen 10 jets in these things staggered, trying to get them even. They're horrible.
Yeah, corner to corner trying to make it,
drill out air bleeds to try to, it's absolutely horrific. And the manifold design is pretty goofy because two things. One, if you look at the flange angle there, here you have this beautiful flange, and then you mill it. Yeah, now you end up with flanges like this. So where before you'd mill a manifold 45 thousandths and drop 50, now it's going to drop 80, 100. So hitting that target of port match is really difficult as well.
Because it moves so much.
Oh, wow. And they're goofy as far as the plenum looks because the runners are way down. I mean, the ports are only that far off the deck. So the runners are aimed way down like that. And the last thing you want to do is have a port like this and put a runner stand up. You want that a straight shot. Now, this is one of my manifolds, and it was the best running manifold I'd ever done. And you can see how I incorporated the offset into the plenum itself.
Yes.
And these billet runners, again, you are working with an angle here on the runner. So when you measure a Hemi runner, you're not actually measuring the cross-sectional area because the flange is like this and the port is like this. So the measurement that you get, that's hard to explain. But again, compound angles. These things.
You gotta like geometry if you're gonna work on one of these things.
Yeah. Runner length. Let's get into runner length a little bit. If you notice, those runners look kind of long, but they're really not because I've milled all the port away. The port's only that long. So you look at that and you think, oh man, that thing's not going to wind to 9,800 RPM. But yeah, it's actually tuned perfectly to 9650 is where that is tuned to. And how do you tune a runner length? I'm just going to get into it real quick. You can go to schwartzracing.com, and he's made this so simple. This is the second harmonic, which almost all sheet metal manifolds are tuned to. If you look over here to the right, you'll see if you want to turn 10,000, you walk over here, and it should be 10 inches.
Oh, they do the math for you?
Yeah, it does the math for you.
I like that.
Yeah. So a lot of times you will, there's two harmonics we use, the second and the third order. You know, the old days in the single plane manifolds, you'd use the third order, and all sheet metal manifolds would be the second order.
Welcome back to the Engine Performance Expo. We experienced a couple of technical difficulties, but Kurt Johnson got on the text machine and sent me a text. Kurt, thank you very much. We've solved the problem, Lake. We've solved the problem.
Well, it was Darin's technical download. It didn't just blow our minds, it blew up the computer too.
Right? Everybody's out there. We're watching. We're getting like to the... Darin is just about to reveal the secret bat cave where all of this is about to happen, and it crashes. But, hey, seriously, we've got some inclement weather in the Tennessee area coming through. Who knows what was the reason? But let's get back to it immediately. Darin Morgan, take it away.
Speaking of all the wind blowing outside, let's talk about airflow again.
Yes.
I think we left off here.
Yes.
Yes.
And basically people, when I talk about orders or harmonics in an intake manifold, people are confused, and I was for a decade, because it's not an easy thing to grasp. You know, the concept itself is what is happening here. Well, basically, it's a reflection of the signal. So when the valve shuts, it sends a reflection, it turns around, comes in, goes back out multiple times. But each time it goes out and comes back in, its amplitude is lower. It has less energy. So you want to capitalize on that and use the first order you possibly can.
So what you're saying is that when the valve closes, the air bounces backwards. So the air isn't always flowing just in one direction.
Okay.
Right? Because I know
it's not.
Well, because I know Kazi's here in the building, right? And years ago at AETC, he showed this video where he had a clear intake manifold runner, right? And put his finger in there, and you can see his finger literally bouncing because it's actually bouncing back the other direction.
Yeah, that is the actual pressure wave.
Pressure wave.
Yes.
Okay.
It's not the airflow path itself. In other words, upstream the air is still moving, but this pressure wave is going back and forth. But it's not affecting the actual molecular flow of these molecules going.
Atoms are still moving this direction.
Yeah, this is a pressure wave that moves back and forth.
Okay.
So the air doesn't really stop. It stops closer to the seat, but the air is continually trying to move into the engine.
But this
pressure wave, the air's moving in, this pressure wave bounces back and forth, and right before the valve opens, it raises the pressure at that valve. But when you open it, boom, you get a hit. You get to start that cycle.
So you're trying to time.
Yes.
No difference. Right? So Dad and I do vintage go-kart, all two-cycle stuff. So we're always tuning the exhaust pipe runner for this same thing, because with a two-cycle, there aren't valves. So you're using that pressure wave tuning as the valve to try to close that valve to trap the air to make the power.
During overlap, when the valve is just opening, there's no piston motion, there's no pressure drop. All you have is the overlap cycle going on. So if you have this high pressure, high amplitude pulse there, you get to start the intake cycle. You get to start moving air into the cylinder earlier. You're not going to make it up. If you don't have a high enough pressure or a lower pressure at this point, you're not going to make it up later in the cycle. You've lost. You need to start it as soon as possible. So the timing of this is perfect. It has to be perfect.
This is one of the ways you can have an engine that can create more volumetric efficiency than 100%.
Yes.
If you don't do this right, you're not going to get there.
And you can achieve trap volumes of 124% volumetric efficiency. So that's 24% more than nature would otherwise allow you if you didn't have these harmonics in the system. As well as, it's a long story, but this is the start. You have to time this perfectly. Otherwise, everything else falls apart. So you have the pressure wave that starts it all, and then all the air starts to accelerate into the cylinder, and then the piston comes around, the valve shutting, but now you've built all this airspeed. You got it started early, you got the airspeed high, and even though the piston's coming up and the valve shutting, the air is still coming in because you built all this airspeed and it's sitting there moving into the cylinder. That's how you can raise the VE. So what I did was I thought, well, how am I going to demonstrate a harmonic for people to look at, or the multiple harmonics? And I thought, okay, well, I'll just go into my electronics lab, and I made a dirty little sine wave that has harmonic content in it, and I just put it up on my spectrum analyzer. So you have what's called the fundamental frequency. That is the cycle of the valve. The valve is cycling at 10,000 RPM. That'd be 83 hertz, 83 times a second. That thing is opening and closing. And that is the first bump you see here off to the left.
Your first order.
Yeah. So this is at 1 megahertz, but it doesn't matter if it's 83 hertz or 1 megahertz. You still have a reflection of the wave. Here you have an electron going down a steel cable at 65% the speed of light, but the reflection, the time distance behavior is the same. The physics are the same. So you want to choose the second harmonic or the third harmonic. Well, we always use the second and the third. The valve is closed, the cycle's taking place. We don't use the first. We always use the second and the third, or the fourth if you're absolutely stuck and you can't use another one. The reason you want to use the first one is the amplitude. Every time that goes out and comes back, the amplitude decreases. So you don't get that hit, you don't get that start. And the reason we use the second harmonic, the second time it arrives at the valve, for sheet metal manifolds. But in the old days, 10 years ago, we used to use the third or fourth harmonic for single plane manifolds because all the runners converged, and you had this nasty plenum area, and you couldn't fit the runner, and you couldn't have runner isolation. The runners were all together, and when you don't have runner isolation, they don't act separately.
Right.
You have crosstalk, and suborder
Yeah.
frequency. You have all this mess in there. So you have to drop a harmonic down. But nowadays we have 3D printing, and we can make these manifolds with runner isolation, and we can hit the second harmonic perfectly. And for truck pull classes where you are dictated, you have to have a cast manifold, which is kind of a dumb rule nowadays, because you can just 3D print anything you want.
Right, back to the rules makers. You're not saving people money anymore.
Right.
Costing them money now. It's not working the way you originally intended.
And basically, if you're a singer, each order is 1 octave. It's a doubling of frequency. So here you have 1 megahertz, 2 megahertz, 3 megahertz, 4 megahertz. Boom, boom, boom. It's just a doubling of the frequency. That's it.
Amazing.
That's awesome.
Amazing. What a great way to start. Day 2 of Engine Performance Expo. Subscribe, click the bell, click share, notify your friends. This was a big time informative deal. And hopefully people are now more interested not only in the Hemi hand grenades, but the whole concept of class racing and trying to take automotive history and make it as great as it can possibly be with our modern technology.
Absolutely. Not only did he blow our minds, he blew up the computer, but we're back and we're running.
Yeah.
And then
What a day, what a day, what a day. My brain is swollen. I've learned so much today. They told us, don't start cars. We are not going to listen.